Hi, welcome. I'm Corey Kell, creator of FlatEarthIntel.com, and today I'm going to give a presentation on putting it all together using the Sun Video 11.1. This is part one of a two-part series, and I'll go over, we're going to talk about why we use the sun, and we talk about the shape of the Earth, and we've got a lot to talk about, a lot to go through, so with that, let's get started. What we're going to talk about is the geometric form breakdown for the globe model and the flat Earth model, or the FE models. Understanding the use of the sun, the equatorial plane in the tropics, and the ecliptic, how that all works for the globe model and the flat Earth model. History's key players when we look at the shape of the Earth, who was kind of involved in some of the testing very early on. What is vertical angle and why it's the answer? A lot of people don't know anything about vertical angle. It's mainly used in military science and civil engineering, the two sciences that use it. We'll talk a little bit more about that. The sun at 90 degrees and what it really means. That's really important, understanding that and why the sun is 90 degrees in both the flat Earth and the globe model. Geometry and triangulation, why it works. It's a very simple geometric process. The Sun Survey Point, the SSP, we're going to talk a little in depth about the Sun Survey Point and what that means when we get to testing the shape of the Earth and the accountability process. And then the two methods of timing, we'll talk a little bit more about the two methods of timing, time set and the sun plot, and we'll talk briefly about them. And with that, let's begin. Let's talk about the globe model basics. And when we talk about testing the shape of the Earth, we need to break the shape, that geometric form, down into 45-degree sectors is the best way to do it, because again, we want to take big chunks of the Earth, and we want to measure it for using the sun. We want to use it up at higher angles, or up above 25 degrees, because once we get below 25 degrees, we get into atmospheric and lensing and some refraction that occurs just based on the Earth's atmosphere, pollution, and a bunch of interference that happens. And you can see this in your either your day or nighttime sky when you look at the celestial body of the sun, or in the daytime, or the moon at nighttime. When it's really low on the horizon, moonrise or moonset, you'll see that object can be very large, especially in October. It gets that big October moon, or the sun. Some of the sunsets, you can see that sun gets really, really big at sunset. So that sun size really balloons up. Again, that's why we want to use the higher angles. We get out of those atmospherics, and military science identifies that. You know, we use survey using celestial bodies to say, hey, you got to step above, out of that zone. So just to stay up out of those atmospherics. So that's one of the reasons we want to use the 45-degree sector test. We stay out of that lower elevation zone. Again, the breakdown for the globe model, we have the sun's operating range, the equator at the center, the Tropic of Cancer in the north, Tropic of Capricorn in the south. 8 45-degree sectors. 8 times 3 being 24 hours, each sector being about 3 hours in sun or orbital rotation time, to give us 360-degree coverage. And again, that's the sun's operating range, the tropics. Just a little bit more breakdown, what it looks like. Again, the OS, you'll see here, that's the observer station, how we can actually how we do the setup when we get ready to measure vertical angle, our position. In other words, we're setting that geometric edge, and we'll talk a little bit more about that in positioning, especially when we test the globe model. The globe model's orbital rotation is counterclockwise, making the sun movement east to west in our daytime sky. Again, 8 45-degree sectors for 360-degree coverage. Very simple, very basic. When we talk about the OS, we're talking about timing tracked by the MARCS device at the Sun Survey Point. We'll get to a little bit more in depth how that creates setting that edge, that accountability. And if we look at why we want to use these rings, and these are kind of like the rings of latitude on the globe model, you know, those are geometric rings, and you can break those rings down into 45-degree sectors, and that's basically what I did. So when I created the 45-degree sector test, the best way to test that geometric form, both models. Flat Earth model, very simple model, flat Earth, 8 45-degree sectors. Again, flat Earth having a huge advantage in vertical angle measurement, meaning the limit is far greater than the globe model for the 45-degree sector test, because you're measuring it from a flat or 0-degree surface, whereas the globe model, you have to account for the globe's curve when you do that test. So huge advantage. But this is, you note that the sun is very small in the flat earth model, very small. It's actually the size of a pin. You wouldn't be able to actually see it, but this is just kind of blown up. And then you have the North Star, the magnetic north. Of course, you have the equator in the middle, the Tropic of Cancer on the inside, and Tropic of Capricorn on the outside to the south. So the flat earth and the globe model have some similarities. Why we use the sun? The sun is 90 degrees to Earth in the summer sun season and during the equinox in the tropics for both models, both the flat Earth and the globe model. That's very basic. The sun is the center celestial body for the globe model. That's why we want to use it. That becomes a primary aiming reference or aiming point, because then we can check that model's orbital mechanics. This can be used to verify the model's orbital mechanics by the sun's position, its azimuth or direction from our orienting station, and height or the vertical angle measured from our orienting station. So it's got to pass those two measurements. Also, the model's sun size at its said distance can be checked if it's 1 degree at 93 million miles based on its geometric form. So we can weigh that said size at its said distance against that geometric form to see if it actually works. And we'll show you how to do that, what that looks like. Test each model's geometric form in the 45-degree sector, in each sector. So we're going to test sector 1 and sector 8. Sector 1 being the westerly and sector 8 being the easterly. So you're going to do two east and west tests. So it's going to kind of balance out. And there's important information about that. Avoiding testing at lower sun positions, 25 degrees and below, excludes lensing and refraction. That can be very easily seen again by the sun size at sunset or sunrise. Also moonset, moonrise. So if you haven't noticed that, kind of take notice of that next time you look at those celestial bodies. What is the equatorial plane? Dictionary.com definition: plane passing through the equator of the Earth or another celestial body. Science direct definition: equatorial plane intersects the celestial sphere and the celestial equator polar axis and celestial poles. The Earth's motion around the sun is then pictured by the apparent motion of the sun in the ecliptic, which is tilted, there's your tilt, at 23.45 degrees with respect to the celestial equator. In other words, that globe model is tilted towards the sun for the summer sun season, based on the position in the ecliptic, and then tilted away from it in the winter season. The angle between the line joining the centers of the sun and the Earth and its projection equatorial plane is called the solar declination angle. We talk about that in my book, Sun and Earth, a Modern User Reference Guide. This angle is 0 at vernal 21 March and autumnal 2023 September at the equinoxes. So again, there's no tilt. That's when the sun's at the equator. The only time in both hemispheres when the sun is at 90 degrees for the globe model. What that looks like, this is a diagram. We have the ecliptic or the elliptic that's tilted like that. And again, as you tilt towards the sun or you tilt away, that's how you get your sun and winter sun season, 23.4 or 23.45 degrees. That's the difference, or the tilt, the angle of that globe model in the elliptic. That's how that model gets its seasons. The sun at 90 degree position, what that means in simple terms, again, which we'll talk about, it's just sun position. In the globe model, it's the elliptic. As that model spins counterclockwise, it moves that sun. If it goes towards the Tropic of Capricorn, of course, you have the fall and winter up in the north, and the Tropic of Cancer in the northern hemisphere, and spring and summer in the southern hemisphere, and where that sun is located. And it does this basically for both models. So it's the same action for both models, except it's just sun position when it's located or where it's located on Earth for both models. So that sun position causes the sun seasons. The only difference is the sun in the flat Earth model orbits over the top of the flat Earth. Basically same methodology. Sun position when it goes up in the northern hemisphere, that's the spring and summer sun season. And then you have the winter in the tropics, in the Tropic of Capricorn, or in the southern hemisphere, that winter, fall and winter sun season. Again, very simple methodology for both models. The sun at 90 degrees is kind of like a lollipop on a stick. That's the best way to describe it. On the flat Earth model, you can see it just orbits over the top of the flat Earth. And you know what that lollipop is, up and down, straight up and down. Where on the globe model here, we see that sun and that globe is in the elliptic as it travels around the orbits around the sun. And it does that counterclockwise spin. It tilts, keeping that sun at 90 degrees. So that's a lot of movement and a lot of motion. That's going to work against that model when we actually test it, because that model, that sun, has to be at 90 degrees. That's why you have these rings. Some people say, well, that 90 degrees doesn't exist. Well, that's absolutely false, because these rings identify that sun being at 90 degrees, or you wouldn't have them. You wouldn't have those concentric rings on that model. So that's evidence for that model, that model has that sun at 90 degrees for that model, that motion of that model. That creates it. Same thing for the motion of the model, the sun over the flat Earth. It's that sun is 90 degrees. That's why it causes those concentric rings above the top of the flat Earth. So a lot of people misunderstand the mechanics of the globe model and the flat Earth model. A little bit more information about this, the summer seasons, winter sun and summer sun. It's basically just a tilt for the globe model. And then the equinox, the only time when the southern hemisphere and northern hemisphere have the sun at 90 degrees, when the sun is at the equator at the equinox. Again, just more information about that. Let's talk a little bit about history and science. When they were trying to prove actually that the Earth was a globe. The Copernican model is the globe model. Copernicus came up with basically started coming up with about 300 and some years ago. The globe model is the Copernican heliocentric model that occurred, and you can see his little diagram there. Then people started doing testing. Samuel Rowbotham does the Bedford-Ludlow experiment, and it actually fails to provide evidence of the curve. So that starts to be a problem. That canal in England failed to provide evidence that the curve existed. I think it was about 6 miles or so, and failed to show evidence of the curve. So there started to be problems with that model, with the globe model. So then science says, hey, we need to do an experiment. Michelson, Morley, two very astute physicists. Michelson wins the Nobel in 1908 for physics. Both physicists. They conduct the Michelson-Morley experiment in 1887. And they get a null answer on their experiment, which means there were no rotation or no movement of the Earth was detected. So that's a huge problem. Now the Earth isn't moving. Okay, so Einstein, they bring in Einstein and say, hey man, we need a theory. Einstein comes up with the theory of relativity, E equals mc squared. Basically removes the ether. He takes the ether out of the equation, saying that, well, you can't detect the motion of the Earth cannot be detected by any physical movement, can't be detected by the eye, by what you see. So he basically removed the ether. Well, George Sagnac comes along and conducts an experiment to provide evidence that the ether exists, and lo and behold, it does. He gets a difference in these fringes. He conducts this experiment in 1914 and says, yep, yeah, the ether exists. And Einstein's like, oh man, okay, another theory. 1915 comes up with another special theory of relativity, but again, really kind of a failure, because science really failed to prove the movement of the Earth. And what it had to do is use theory. And again, then after that, we start to get into science. Science fiction comes along to kind of help the heliocentrists out and say, well, you know what, we're going to sprinkle in fiction with that model to make it work and make people believe in it. And that's what happened. That's what occurred. The individual who saw this happening was Nikola Tesla. He called out the heliocentrists and he said, today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relationship to reality. In other words, he's talking about the sky and the globe model. That they made it mathematics, and he said it's not mathematics. It's for signs, seasons, ambience, and beauty. It's a clock. It's a clock system. Tesla called him out hard. He knew what was going on. What Copernicus would add to verify for the globe model, directional azimuths. Directional azimuths, they kind of work. We get those to work, but vertical angle becomes a problem. The height of the luminaries, especially the sun in the sky, it's too high in the northern hemisphere in the summer sun season. So that's a huge problem, especially around the summer solstice. There's quite a great difference there, and that's a huge problem. So vertical angle fails. What that does is it causes failure in the orbital mechanics. In other words, the orbital mechanics fails because you have to have direction and height both work, and they don't. However, they do work in the flat Earth geocentric model. And that's a huge positive for the flat Earth model. The sun's position in the sky seasonally, it's too high in the summer sun. Again, fails. So huge problems in heliocentric model. What works against that heliocentric model? Distance. Once you exceed the limit, the farther you go out from this model, the farther you go off the line of parallel. Line 1 being the sun at 90 degrees. Remember, the sun is always 90 degrees in the summer sun season. That's when we want to test it. That line of measure, line 2, has to include that line of measure. As for the 45-degree sector test, if you're doing the 45-degree sector test, this has to be 45 degrees and this has to be 45 degrees. So that equates to 90 degrees. That model would pass, but if you exceed it, which it does on both sides of terrestrial Earth for the summer sun season in the northern hemisphere, I've tested on both sides, it vastly exceeds it. That excludes, we can then exclude the globe model because it fails. It fails its vertical angle. In other words, the summer sun is too high. And the farther you go out, the greater distance you get. And that becomes a huge problem. The equatorial plane, again, the sun's operating range, you have to know the limit. Got to know that limit. I had a 5-hour conversation with a professor of science out in California and couldn't identify the limit. If you're 45 degrees, what's the limit? What's the max vertical angle your limit can be? He wouldn't identify it. 3 weeks later, he called me up or he emailed me, said, yeah, it's important. You got to know the limit. So it weighed heavy on him. So I know that it bothered him because he contacted me 3 weeks later and said, yeah, it's important to know the limit. And you have to, especially when you're testing the model. The globe model spin, the sun is out of position in the daytime sky. This also tells us that the spin or the orbital rotation does not work for this model. This means that the sun is orbiting over a flat stationary Earth. That's the simple of it. Again, the rings of latitude, they become huge problems. I know that professor, he sent me a short video, about 2.5-minute video on using the globe, and he tilted the globe on its side, and I'm like, look, I'm seeing all these rings of latitude, and I'm thinking, I'm going to show you some things about the rings of latitude you've never even encountered before in your life. And that's what really got him in trouble, because you have to account for that surface angle, especially if you're measuring from the globe on, you're testing that surface, you have to account for that angle. And again, that becomes a huge problem. These rings of latitude are a big problem. That surface angle is huge. Measuring distance, surface angle. This is what I'm talking about. If you're OS, if you're located here and you're measuring the summer sun at the Tropic of Cancer here, your position for this one would be each one of these squares is 10 degrees and surface angle, and you basically count the squares between your position and the sun, which is 5.5 squares, each one of these being 10 degrees, so that'd be 5.5 or 55 degrees, meaning if you're here, you're at this position, you are 55 degrees angled to the sun. In other words, before you even start measuring the test, you're 55 degrees. So now you can only go up 35 degrees to get it to 90 degrees on your vertical angle measurement. And that's a huge problem. That's a very small vertical angle. And again, that surface angle creates havoc for the globe model. And again, that's why the flat Earth model has a huge advantage. This concludes part 1 when we talk about using the sun. And I'm Corey Kell, creator of FlatEarthIntel.com. Thanks for watching.